So the UR5 manipulator has got 6 joints, and I'm kind of blanking on where they are, but there are six DOFs. And then some point there is like a end effector. There's no real end effector placed in the file we're dealing with, but this end effector, the position of the end effector can be computed, XE, YE, ZE, and then unlike the planar manipulator where you only talked about X, Y, and the orientation, here we have to deal with 3 orientations. Let's say phi, let's call that PE, theta E, psi E. And the IK problem is compute, let's call these names, let's say 6 degree FR, Q1, Q2, so on till Q6. Compute Q1, Q2, Q3, Q4, Q5, Q6, such that XE minus XREF is 0, YE minus YREF equals 0, ZE minus ZREF equals 0. So those are the 3 positions, and we also need to ensure phi E minus phi ref equals 0, theta E minus theta ref equals 0, and psi E minus psi ref equals 0. Okay, now there is a problem though. This could be problematic, okay, because of singularity. The Euler angles is not a good way of representing the orientation. So I will show you how what happens. We'll try this out, but there are other ways we can do that last matching of the orientations. One is using the quaternions. So what you can do is you can convert phi E, theta E, psi E. These are the orientations of the end effector, right? This is something which you can compute given the Q1, Q2, and so on. What we'll do is we can convert these to, let's call that Q, I think the notation I used was Q0, but we want to put the E. So let me call that, that's a good way of writing this, Q, QE, we put 0, QE, 0. No, but let me just put Q0, QEX, QEY, QEZ. So this represents the 4 numbers associated with the quaternions. You can do that. And then what we'll do is the last 3 conditions, so last 3, which is, these are the last 3, we'll change them to the following. So there are 4 quaternions, but really we know that the 4th one is this. Before there are 4 quaternions, the norm of that vector of the quaternion is 1. So really there are 3 numbers, unique numbers. You can choose any 3 of them. So what we can do is we can rewrite the last 3 equations as QE0 minus QREF0, QE, well, actually let's do X. You can choose any of them. Any 3 will do. But just to be consistent, we'll just use X, Y, Z. So we also would obviously need to convert, if you're given the refs in terms of angles, we need to convert them to quaternions. So if you are given ref, theta ref, psi ref, you need to obviously convert them to the quaternion ref 0, quaternion ref x, quaternion ref y, quaternion ref z. And that would be the last three. Now, there's another way to do it, rotations. So we can then convert the same three things into rotation matrices. Let's call this RE, and then this is RF. Okay, now how do we convert? How do we write those last three conditions? The rotation matrix is a 3 cross 3 matrix, right? And RF is 3 cross 3. So we have actually 9 numbers there. So how do you use? We only have to define 3 conditions. So one way of doing that is to notice that when the two orientations are in line, that is, you will have RE will be RF, right? This is what we're trying to do. But these are 9 numbers for the 9 quantities in the rotation matrix. So what you can do is you can, we can pre or post multiply, let's say post multiply by RF transpose. So RE RF transpose equals identity. So what we have here is 1 0 0 0 1 0 0 0 1, and you can check any 3 of the numbers there. You don't have to check 9. Okay, just works out right. So one way of doing that is the 3 conditions could potentially be like this. Or last 3, I'll just write it as last 3. So the last 3 conditions I would write as RE RF transpose. So I use the Python convention. So I start with 0 0 is my first element. So 0 0 should be RE RF. Whatever. We write it as I comma I minus 1 equals 0, where I equals 0, 1, and 2. So what I'm trying to do here is effectively I'm trying to take the diagonal elements, that's the diagonal element, and trying to see that all the diagonal entries as 1. So those last 3 conditions are just those 3, and that will work too. So I will write the code, of course, but you have 2 ways, well, 3 ways of doing this check. One is rotation matrix, quaternions, and Euler angles. Euler angle, my claim is, will not work sometimes. It could work, but your better bet is to use one of those last 2. So these are the preferred ways. Okay, so with that, let's try to do IK for the UR5. So what I'm going to do here is I'm just going to start off a file which I created some time back. This was the forward kinematics for the UR5. I'm just going to modify that file, and that'll be the fastest route instead of trying to write from scratch. So I'm just going to call this inverse kinematics. Okay, and then let's rename this. Okay, and then I'm just going to get rid of this file. Last time when I did forward, I did it with my own code, which was the animation was done by me in a separate file. I'm just going to get rid of this. Okay, what I need is to rename this. This will be the main function, which will call other functions. Okay, and let's work with this. So need this. Okay, and let me run this to show you what it produces. It basically will given a joint configuration, joint angles, it will do animation of the manipulator. Okay, so that's that. And then the other thing which this one does is it essentially writes down the end effector position given by MuJoCo, that is the MJ, and then the one which we got from our own calculations using the homogeneous transformation. So that's that. Now we're going to modify this. So what I'm going to do is I'm going to use my calculations to do the inverse kinematics. So I don't want it to show, I don't want it to do all these things. Okay, I will do those calculations in the back end. And then when this is printed, it should basically print the inverse kinematics solution, and I'll check it with what I get, whatever I asked to compute. Okay, so first things first, let's try to specify end effector position. So let me, there's some values I already used before, just use those. Okay, so I'm going to use the following reference. Okay, so xref 0.5, yref 0.2, zref is 0.5, phref 3.1400, and then xref is what I'm trying to achieve. And if everything works right, then the end effector using my calculations should also be, that is after doing the inverse kinematics, should sit at xref. There's a way to visualize this particular thing. Now, this is basically giving you the orientation of the end effector, right? Right now, when I run this, it's going to be the same thing, but there is a way to visualize the frame, and that is, there's an option called, so if you remember when you did this XML to design the viewer, you showed the frames. Turns out that you can show frames using opt.frame, MJT frame, frame site. This is actually one of the structures within MuJoCo. So if you run this now, it will actually show the frame on the site. So run this. So it shows the frame. Okay, you can change this to world frame or body frame like this, just to world. Then it will show the world frame. Then there are other options. So the way I've put a comment here, if you wanted to show, I think body is what you will say. It'll give, if I'm not mistaken. Yeah, so it's showing this, and the body, you cannot see them because it's hidden. But the way to check this is to go to this link, and then it actually gives you a bunch of options on what other things you can do. It's going to be part of the file, so you can click it. Okay, so you've put this there. This is the xref. Now, let me first show you. Let me just print the. So if everything works out, this should be equal to xref. So let me just print that. Print. We call that reference, and then reference quote. So the reference is something which I specified, x ref, and it's going to be the first three elements. So when you say this goes from 0, 1, 2. Now this is quaternions. I need to convert the reference from, I've given the reference as Euler angles here. I need to convert these angles to quaternions. So inside the utility file, I have a way to convert that. So I'll call that ref Euler equals, I need to convert from Euler to quat, and then I need to supply it with an array. So this would be phi ref, theta ref, psi ref. And then if everything works right, then it should print ref Euler. Okay, so now I'm going to run this. What is interesting for me here is right now what is provided by this. So this is where the actual manipulator is. It's 0.49, 0.13, 0.48 for the given joint angles, but I want to go at 0.5, 0.2, 0.5. So you can see it's kind of not too far away. 0.13, 0.2, and 0.48, 0.5 is not far. But if you look at the Euler angles or the quaternions here, this is, I wanted to be at 0, 1, well, I wanted to be at 0, 1, 0, 0. It's actually pretty close, 0, 1, 0, 0. So this will make my life easy because if I have the start position very close, it's going to be there. But let me make my life hard by choosing a different Q. This Q is way off. So that will really push the solution which we're trying to obtain. So now it's going to be way up, which means that if you now compare the end effector position, this is where the actual end effector is way up compared to where I want it to be. And now we're trying to see that we can get it back to here. So now let's start working on the code. Okay, what I need to do here is there'll be a single thing I need to do. I just need to essentially call the fsolve and provide it with this parameter. So let me define fsolve. Fsolve, I will write a function called inverse kinematics, and that function will input q. This is the initial guess. So that initial guess, I already have it here. All right, and then it'll basically be updated. And then once you solve it, you really have to solve the same thing over and over again. And then I need to pass some arguments. This will be the reference. Okay. So if everything works right, this will provide the queue, and that queue will be updated. And then hopefully this thing here, the MuJoCo, the way MuJoCo understands the end effector position will match with the reference. Okay, so I just need to write this. So let me first import fsolve and import inverse kinematics, and then I'll try to write the function fsolve. So to import fsolve, two things, I'll just take a shortcut here. I already have defined them here. So I need these two things. Okay. This function needs to be defined. So file, Python file. Always need that. Def inverse kinematics. Okay, now what are the inputs? Well, Q is the one input, xref is the other one. And then what I need to do is unpack xref, provide what needs to be zeroed, and return it. So it will return something which is to be zeroed. So the unpacking, which I will save some effort here by just taking it from here. Okay, so that's basically unpacked at xref, yref, zref, so on. And then when I return it, when I need to return it, it'll be some x, which I compute, or xc minus xref, y minus yref, z cref. And then I said there are a couple of options. Phi minus phi ref is one. Let me write that down. Psi minus psi. Okay, so this will be returned. What? Oh, let me save this. Let me call this inverse kinematics.y. Okay. So the only thing I need to do now is to figure out x, y, z. That is what I get if I run through the forward simulation, the forward problem. So here, actually, I've done this work for myself. I have the code which I generated last time for forward kinematics. I just copy paste that. Yeah, there it is. So this file actually provided me with the forward kinematics, which is something I wrote down, and then it gave me the end effector position, rotation, and the quaternion. Let's take this, put it here. Okay, so it doesn't understand this, and it doesn't understand that. So I need to import those things. Okay, the fastest way is probably here, right here on top, both of those things. So I'll take this one. That's the utility file. Then I'll take forward kinematics. Okay, and then hopefully it won't complain now. Okay, so this one produces the end effect position. So if I want to compute x, that's simply y end. That will be the 0th element. And then y and z are straightforward. Y, z, so 0, 1, 2. And then that will go here. So we have taken care of this. Now let's get phi, theta, and psi. Now this function produced us with the rotation and then the quaternion. So we still need to get the Euler angles. So I think I have a utility called rotation to Euler, and then I need to provide it with rotation. So okay, so then phi will be phi 0, theta will be phi and effector Euler 1, psi will be okay. So that completes it. There's nothing more to be done. I just hope that this will work. Let's see if we get the IK solution. So it should be, oh, it worked. So that's interesting. I think it worked. Let's see. We can check it. The way to check this is to just look at what we got for output. So, oh, well, it did not work. So the IK gave us this solution, 0.33, 0.02, 0.42, but we need it at 0.5, 0.2, 0.5. So though it looks like it's there, it's not quite there. And then the Euler, the quaternions, it was just off. So this does not converge. In fact, there's a way to get the properties. So fsolve actually tells you if it converged or not, and I would leave it to you the next exercise. It returns more things than just that cube. It returns some of the properties like did it converge or not, and you can look at the documentation. So I think the reason is because we are using Euler angles. Let's try to use quaternions. It's already there. We just have to use it. We already have computed the quaternions. So the next way, I think this fails because of problems with the Euler angles. Let's change this to okay, I need to get the quaternions for the reference, which is not there. So xref, I have these. So let's do that. So first thing I convert quat ref, that would be Euler to quat np dot array. So I have phi ref, theta ref, psi ref. So I have quat ref, and I need to get, I already have the quat here. Okay, so what needs to be done is, you know what, let me just do it slightly faster. It for I in range 0, 3, 0, 1, 2, 4, sorry. The quat equals minus quat ref I, and then t quad is going to store the difference. T quad equals np dot zeros 4. So initialize to 0, and then I get the difference. And now let me just put it here. It's easier this way. Okay, so d quat 0, e quat 1, e quat well, let me use 0 is the constant one. Let me use the, as I wrote down the notes, the x component, the y component, and then the z component. So it'll be 1, 2, and 3. Ignore the 0th one because that's a constant. 3. Okay, let's see if this works. It looks the same. Let's quit this. Yeah, there it is. So the end effector is 0.5, 0.2, 0.5. I have 0.5, 0.2, 0.5. And then 0, 1, 0, 0. It's almost close to 0. It's, I know it's like 1e negative something, but that's the same thing. So this actually does give the inverse correctly. Okay. We can also use the rotation. Okay, so the rotation is, I need to convert this to a rotation matrix, ref. So Euler to rotation, and then NP, same thing. Okay, once I get that, I already have the rotation matrix for this. Where is that? Here it is. Okay, so I need to do R times R transpose of ref. Let me do that. So I'm trying to do R times ref transpose. Now that should be identity 3, right? So that would be, let me just save it as RRT equals, so it will be, I do this R, it will be pi. Okay, that times R ref. I think this should be, then this will change. As I put in the notes, it should be RRT 0. And then 1. And then 2. Interesting. It did. Oh, yeah. Good catch. Yeah, should be -1. That's why it gave the incorrect answer. Okay, there it is. So let's put this. So this is what actually it is, MuJoCo thinks, and this is what actually I'm getting. Well, this is what it should be, reference, which I provide, and this is what MuJoCo thinks it is. So it lines up. So that's how you do IK.